Welcome to yet another video on the Technomura channel. We hope you, an electronics or vintage enthusiast no doubt, will enjoy it right from the start. Give us a thumbs up if you liked it, leave your comments down below, and please subscribe if you haven't done so already. So now, let me introduce your host for today, Technomura.
So, this is something unexpected. Rather than do one of my, let's say, usual projects like restoring a radio or a tuner or a TV or something like that, I was approached today by somebody whom I think is the owner of this guitar amplifier. It's actually a Marshall MG30 DFX. Yeah, you can see there the logo. Now, the guy approached me and told me, listen, when we plugged in the amplifier, all the fuses of the locale where we were just blew up. Yeah. So I thought, oh my, that could be a serious problem. I'm not sure, of course, but in any case, that's what he told me. And he told me when they plugged the amplifier in another power outlet in the building, all they got out of it was a very loud hum. This is the back of the Marshall amplifier, and it looks pretty much like, I would say, a classic guitar amplifier. Okay, a simple wooden case, which is plastic covered with the usual corner braces you see there. Okay, and inside the 10-inch speaker right there. So there's not much to it actually. I had a look inside because this tray here is obviously where all the electronics are housed, and I could find no screws on the inside of the case to keep the tray inside the box, as it were. But I did spot this. So it's rather heavy. I would say about 20 pounds or so. So what the case does have, okay, is screws on top, which are not part of the braces. So there's another one here, and then on the other side just the same thing. So a screw here and a Phillips screw there. So my guess is to take out the electronics part of the amplifier. What I need to do is disconnect the speaker, and I think, I'm not sure, but let's have a look. Oh yeah, the amplifier has easily disconnectable wires towards the speaker, yeah. So I just need to pull those two connectors and then undo the 4 screws at the top, I believe, and then we can slide out the whole electronics part. There's a big transformer with two 16.5 volt outputs, and by the way, this is a 220 volts AC transformer. And then there's one long, very long PCB on the inside with a whole bunch of pots soldered to it. Alright, so I had a chat with the owner and we agreed on a price for the repair of his amplifier. So I guess the first thing we need to do to get to work on it is to take out the PCB, and the PCB is held into the chassis with 2 bolts on either side, so well, with 1 bolt on either side, so one here at the back and another one right here where the power from the transformer comes in. But it is also held in by all these knobs and connectors. And I counted them, and in total there are like 14 things to undo. Okay, so 4 jacks, 6.5mm jacks, so 2 on each side of the front panel, and 10 knobs. So I've got my work cut out. So I undid all the nuts from the front and the back. So now I'm pretty curious to see whether we can simply pull it loose. I mean the PCB, of course. So let's have a look. It would seem so. So let's tug it gently backwards and see whether we can undo it or release it from the case. Ah, okay, there's one more little connection to undo, and it's the grounding you see here. Okay, let me get rid of that and then we'll continue. Alright, I undid the grounding wire, which is attached to this little screw, which has been locked into the chassis, in fact, or pressed into the chassis. Now let's see whether we can lift up the PCB and have our first look on the underside of it. I'm really curious to see. There you go. Whoa. This is ooh la la. Yeah, I immediately see a problem. Oh yeah. Before I start work, or any further work on the amplifier's circuitry, I will take out this little circuit here. And although the print board doesn't exactly say what it is, I think, some sort of sound effect board. So I unmounted the little board, and to do it safely, you actually need to squeeze the little plugs you see here that fit through these 3 holes you see on the PCB. So you have a hole here, and another one there, and a third one over there. And it's way much simpler and way much easier if you squeeze these little standoffs together underneath the large PCB. You squeeze them together, and then with duckbill pliers, you know, some pliers like these, you just squeeze them gently together and then push them a little bit upwards so that they're almost through the large PCB. Yeah, almost out of the large PCB. And once you're there, with some gentle rocking and lifting, you will manage to undo the little PCB. Obviously, you should do the lifting and the rocking at the side of the connector, okay, so this side here. So you should gently rock back and forth and at the same time lift the whole PCB. And it comes out fairly quickly. I want you guys to enjoy this as I am discovering it. Now, like I said, something inside the amplifier shorted, okay? And I've been observing and doing some measurements and stuff like that. And I want to draw your attention to this. If you look at this trace here, if you look closely, you see there is no more trace here. The trace is actually gone, vaporized. Now if you go over here and you look here, it's exactly the same thing. The trace is completely vaporized, is gone, completely gone. So yes, there must have been quite some current running there, and through those traces in fact. And if you look at the chassis, well, okay, hang on, I've got some interference from the lighting. So if you see here, yeah, this is exactly the spot below the PCB where you see the burn marks on the PCB. Well, there was a gap here of, I would say, about 10 millimeter between the PCB and the actual chassis ground. So can you imagine a spark jumping like 10 millimeter? That must have been a huge spark, okay? So yeah, obviously something went seriously wrong. Now I did measure the transformer. I measured its primary, it's okay. I measured the secondary, that too is okay. It measures, let's say, the expected ohmage between the common and the two output wires. In fact, the secondary is something like a little bit less than 1.2 ohms between the two outer windings. And if you measure between one of the outer and the common, you get about 0.6 ohms, which is okay. And the primary of the transformer measures close to 49 ohms. And there are no shorts to ground, okay, so to the ground of the AC plug. So, which is great. So yeah, the transformer seems to have survived the ordeal, let's say. Now, one thing I did notice, there is in fact a fuse inside this amplifier, and the fuse is in this housing here, right here. But what I did, I had a look at the fuse. The fuse is good. It still conducts, it's perfect, but it's a 500 milliamps fuse. I mean, that's good for, let's say, an amplifier that would go up to 120 watts or something like this. This amplifier is rated to 30 watts output power, not 120. So yeah, this fuse is, in my opinion, just a bit too heavy. Yeah, I think what would be more appropriate is maybe a 150 milliamp fuse here. Yeah, not a 500 milliamp. So yeah, that too I measured. I also measured the rectifier bridge diodes, which are these diodes here. These are high current diodes. I have to look up the precise type number, but in my opinion these are 10 amp high current diodes. Now, two of these I find are suspect. So these two here of the diode bridge, in my opinion, are suspect. So I need to have a look at those two. And I do believe that at least 3 or 4 capacitors are bad. In fact, the capacitors you have on screen right now, so this one here, that one here, those two are 1000 microfarad 25 volts, and these two here, which are 47 microfarad 63 volts. So I do believe those 4 will probably need to be replaced, and then maybe this one here as well. Yeah, and by the way, this one. So in total, I do believe I might have to replace at least 6 electrolytics. Now, I have no idea whether the output stage still functions. In fact, the output stage is the IC, which is below this heatsink here, and it's a TDA 2050. Okay, so yeah, I have no idea yet whether the output IC still works or not. Otherwise, the op-amps which are on this PCB are fairly common. The op-amps which I found on this board are actually TLO72s, which are very common dual op-amps. You know, like these little ones right here. Okay, so yeah, those are fairly common. There are a couple of ICs on this board which I haven't seen yet, but turn out to be op-amps. Well, at least one of them turns out to be an op-amp, which is this one here, I believe. I think it's indeed this one. This is an NE5532AP, and I looked it up, and it looks to be like a low frequency, low noise dual op-amp. So it might be compatible with a TLO72. I don't know. I need to look it up. Now, there is one slightly more quote-unquote exotic chip in here, and that's this, let me see, is this a 14 pin or a 16 pin? 1, 2, 3, 4, okay, 16 pin. This 16 pin chip here, yeah, is in fact a quad analog switch chip. So you could say, in effect, it's like 4 tiny audio frequency switches, you could say, are built into this. Obviously, not mechanical switches, but more like solid state switches, but even so. So basically what this chip is like 4 analog signal switches. Okay, so let's check whether the primary of the transformer is still good. So I switched the amplifier on, I think, yeah, So let's measure the primary. We know the fuse is good, so we touch one pin of the multimeter to one end of the connector, then the other. There you go. 45.3 ohms. Okay, so now let's see if there's a short from the transformer to ground on the primary. This is the ground. Nothing. Okay, so nothing. This is the primary, other end. This is 45. Okay, so we know there's no short between the primary and ground. So now, excuse me, let's measure the secondary of the transformer. So the common, or the center pin rather, of the secondary of the power transformer is this black wire here. Okay, each end of the secondary are those two red wires here. So let's measure between the center tap first and one of the outer pins. Okay, so here we go. Center tap, outer pin. Come on. .7 ohm. Okay, now let's measure between the center tap and the other end of the secondary. .7 ohms. Okay, now let's measure, say, between the center tap of the secondary and ground. So where's the connector here? Okay, so the center tap is right here. Okay, now let's measure between the center tap and ground on the connector. Okay, open. Okay, so there's no connection there. Now let's measure between the center tap of the secondary and the input of the primary. Open. Okay, so there are no shorts in the transformer. That's a good thing. So I formulated a plan of attack, you could say, and what I'm going to do is I'm going to replace the electrolytics on the section for the power supply. So from this end here to about this end here of the PCB, this part here is the power supply and the end stage of the amplifier. So we're going to replace all these capacitors you see here. Alright, all the capacitors have been replaced. Okay. So the next step is to have a look at a few other peripheral components like the diode bridge, or more specifically the diodes, and a few of the resistors and capacitors around the amplifier stage, which is this chip here. My instincts tell me that this TD8 2050, which has 5 pins, as you can tell, has already been worked on in the past. I mean, you can see those telltale signs of rosin that are still left on the board. And if you look at the overall condition of the board, which is far, far neater, then I would say that most probably the chip, which it is, that does the amplification, has already been replaced in the past. And actually the voltage regulator, which is a 7805 at the back, which is there, mounted there, okay, has probably also been replaced. I also replaced one power diode. Now, the diodes, the original ones, are rated for 3 amp forward current. I didn't have those, but I do have a 10 amp forward current rated diode. So yeah, unfortunately I had to use a 10 amp diode, but I think that'll be okay. So yeah, I replaced that one diode because, I don't know, it measured somehow a bit weird. So, and rather than, take a risk, I'd rather place say a 30 cents component on the PCB and be safe than be a cheapskate and run the risk of having the whole power supply blow up again. Now, I'm doing the same thing with the Zener Diodes. You see over there, these two here, were originally mounted right here. Now, these are actually at the, you could say, the output of the power supply. Yeah, and the power supply supplies a symmetrical voltage, so either plus or minus 15 volts. And these Zeners would regulate that voltage. Okay, now I do have 15 volt rated 1 watt Zener diodes, and the code for those Zener diodes is 1N4744. Okay, so those are 1 watt rated 15 volt Zener diodes. Again, I'm not going to take any risk, trying to skimp on a few relatively cheap parts. And since they were in the middle of the brunt of that power surge, I just don't trust the original ones anymore. They might still be good, but I just don't trust them. Okay, so the two Zeners I just replaced are these two here. And by the way, most of the components that I replaced are the electrolytics located in this area of the power supply. Okay, and then one of these diodes in the rectifier bridge I also replaced. So yeah, so that's what I did. Now what I'm going to do is repair the burned out traces. Alright, so I cleaned the spots right here and here and here and here. Well, when I say clean, I actually cleaned it with some alcohol on a Q-tip, and then with a very fine surgical knife like this, I very carefully scratched away a little bit of the green protective lacquer on the remains of the trace, the original copper trace, to bear some pure copper to solder to. Now, I'm going to try something I've never tried before, but I'm going to try to recreate part of this trace and this trace with some special copper tape. Tape like this, okay? I have them in fact in different sizes, in different width. You know, this is the narrowest type of tape that I have, which is, if I'm not mistaken, 5 mil wide. Okay. Now, what I actually need to do, so this tape is adhesive on one side and is pure copper on the other. So what I need to do is to cut a tiny sliver off of this copper tape and then place it right there. Let me take a pointer, so right there, okay, to replace this part of the trace that was blown away, and one tiny sliver here. And when I say tiny sliver, the width of the tape, so this width here, yeah, is probably not more than 2 millimeter. Same here, okay. And the length of it is probably not more than 5 millimeter, either here or there, okay. So what I need to do is to effectively cut off a tiny little sliver off of the tape, of the end of the tape, then stick it to the PCB and then try to solder it. Alright, so I cut off, as you can tell, a tiny little sliver off of the end of the copper tape, okay. Then I transferred it to the PCB by sticking it to by sticking one of its ends to the tip of my surgical knife, okay, which is a very sharp pointed little knife, and I applied it ever so gently on the PCB right here, okay, right where it needed to be to close the gap. And what I did then is to gently, ever so gently, with a flat screwdriver, flatten out the tape, okay? So to flatten it out so that it sticks perfectly to the PCB. And I think I succeeded pretty well in doing it. It's a very finicky job, but I think I managed. So what I need to do now is put 2 solder points at each end of the tape. So one here and one over here. And that should fix that trace. Now, you shouldn't heat the copper tape for too long, too hard, okay, because it's really actually rather thin copper, okay. So give me a moment to try it, and then I'll show you the result. Okay, it's done, and you're looking through a magnifying glass, okay. In fact, through the same magnifying glass I worked with to repair this. So there you see the result. This is the new trace as it is now repaired and it looks quite clean. I like the result. It's really nice. Okay. Yeah, I know you probably think these wires are touching or something, but no, they were like this originally, and I'm not going to mess with them. I looked underneath, and there's no bridging between this little stub here and the trays underneath, so that's okay. So all I need to do now is clean this up a little bit with alcohol, and that's it. So now we move on to the other trays. Alright, so I'm going to show you how I actually cut and placed the copper replacement trays, as it were. So you see, this is wood. Okay, this is a wooden plank, let's say, and I clamped the end of the tape with a little clamp so that I know it won't slide away while I cut. Now it's imperative to use an extremely sharp knife, preferably like this. I mean, you could probably use a box cutter knife, but I like to use these surgical knives because they are incredibly precise and very thin and extremely sharp. So I am going to do this by sight. Okay, so I can't measure thicknesses of less than a millimeter anyway, so I'm going to place my knife on the end of the tape like this, yeah, and I just apply pressure on the knife and rock it back and forth. There you go. You see how the tape releases at the end? So what I do now is I flatten it out a little bit like that. Now I need to have a look through the magnifying glass because this is clearly too small for me. Okay, so now we're looking through the magnifying glass. Okay, so what I'm going to do now is slide the point of my surgical knife underneath the tape. And this is a bit finicky because it's extremely thin. There you go. So now, come on. Yeah. There you go. Okay. So now the tape is stuck to the end of the surgical knife. So what I do now is I transfer it to the PCB. Okay. And I don't know if you guys can see this, but I'm going to place the copper tape right there. Okay. Right there, and I lift it gently up with the knife and work it to its final spot. You need to take your time to do this, okay? You can't rush this, but this is really a job that takes a lot of effort and concentration. Oops. Yeah, so you can tell that it's not very easy, but if you take your time and you stick it like that, okay, we're almost there. Okay, now I'm a bit lost. Now I need to find out which side of the tape is sticky. Okay. Oh, yeah, I need to do this with two hands, guys. So give me a moment to show you the result once I'm done. Alright, so I stuck the tape and I'm going to try to film it like this, okay guys, and I'm going to use my camera as the lens, in fact. So you take a flat screwdriver like you see me use right now, and what you do is you tap gently on the tape and then stroke it ever so gently, yeah, like that. There you go. Okay. Okay, I think this is good. So what you need to do once you're done is check whether the replacement trace is not making any sort of contact with other traces. And I think we're pretty clear. Yes, I think we're clear. Okay, so next what I need to do is solder the new copper trace to the existing ones. Alright, I'm going to show you how I solder the trace, okay? But I'm doing this, actually I myself am doing this through the lens, okay? So here we go. I hope you guys can see this because it's extremely small. There you go. That's it. It's done that quickly. Let me show you the result. Come on, focus. Yeah. There you go. That's the result of the solder point. And you can see it's fairly clean and nice. So I would say, yeah, both traces are repaired and functional again. Great, so now we can move on to the next step of the repair and test out the power supply. Alright, so I connected the amplifier board via its plug to my variac, and the variac is outputting for the moment 69 volts AC, and as you can tell the amplifier is not drawing any kind of current, okay, so the current is the green numbers, so there's virtually no power being drawn. Okay. Now the amplifier board is on, you see, the LED is lit, okay. So here's a little mystery for you. Now if you look at the schematic, okay, of the power supply, then you see it's pretty much symmetrical, and that's what it was always intended to be. So you have an output of plus 15 volts and an output of minus 15 volts, okay? Right. Now, keeping in mind, of course, that I'm sending far less voltage through the power supply, we're getting, of course, far less voltage from the transformer. Now, I calculated that it couldn't be much more than 5 or 6 volts with 70 volts AC going into the transformer. Okay, so let's check. I said 5 or 6 volts, so if we measure the voltage from the common, which is the center pin you see drawn here, okay, so the common is W3, this one over there, and that one is in fact connected to the ground, and I did that. Okay, so I'm measuring from the ground. Okay, so if we measure from the ground to the cathode of Zener Diode 1, which is this Zener diode here, we should measure a positive voltage, okay? And since we're sending far less voltage through the amplifier for the moment, it should be, I believe, about 5 or 6 volts. Okay, let's measure the voltage at the cathode of ZD1. Okay, well, ZD1 is this one right here. So let's see what the voltage is there. ZD1. There you go. And I'm getting 2.66 volts positive. Okay. Now, since the power supply is symmetrical, I should be getting therefore around about minus 266 volts at the anode of the Zener diode ZD2. Okay, so ZD2, and we measure at the anode of ZD2, which in fact is this wire. So right here, this is what I'm getting, plus 0.46 volts. Okay, that's weird. Okay, now it should be negative, and it's in fact it's showing a positive voltage of a bit less than half a volt. But it should be minus, say, 2.6 volts or something like that. So that's not correct. So, why don't we measure, let's say, around C52, okay, right here. Okay, so C52, and we measure the cathode of C52. So that capacitor right in the center of the screen, okay? So we go to the other side. Okay. So see the cathode of C52. The cathode of C52 is right here. And there we measure minus 5.8 volts. Okay? Okay. Fine. So, we know now that we get minus 5.8 volt right here. So what if we measure the voltage at C56, the cathode of C56. Okay, right after this 150 ohms resistor. Okay, C56 is that one. Alright, so that one here is C56. Okay, let's measure the voltage there at the cathode. Okay, so the cathode of C56 is here. What am I getting there? Plus 0.46 volts. Haha! Now, there is a resistor of 150 ohms, okay, between C52 we measured and C56 right here. There is this 150 ohms resistor. Okay, where is that resistor? That's R59, and R59 is this one right here. Okay, now if we measure on one side, which is close to C52, okay, so we measure here, I get minus 5.8 volts. Now we measure on the other side of the resistor. I get 0.463 positive. Now, you don't have to take my word for it, so let's see. The other resistor is for the positive rail of the power supply, so if we measure here, we should be getting plus 5.78 volts. So that's R59. Okay? Okay, 5.8 volts instead of 5.79 volts. Well, there you go. Okay? So close enough. Now let's go to the other side of the resistor. There. Plus 2.68 volts. So you could say practically half of the voltage. Okay? If I measure the output of the other resistor, yeah, instead of minus 2.68, I get plus 0.46. So yes, there's something not right here, and I need to figure out what it could be. Could it be the resistor that's bad? So could it be this resistor here? Or could it be the Zener that's bad? This one right here. What I ended up doing is I ended up unsoldering this power resistor here, which is a 2 watt 33 ohms resistor. Okay, and in fact on the schematic, this resistor, okay, so this one here is marked as R28, which is come on, focus, which is this one right here. Oh, right here. Now let's track down. So you see R28 right here is connected to the positive side of the power supply. Okay, and its other side leads to a power regulator chip, which is a 7805. This chip effectively makes sure that the output is always precisely 5 volts positive. So I disconnected this resistor completely, and the voltages at the Zener Diodes, so right here, let's reduce the screen a little bit. So the voltages here and here became symmetrical in polarization, so you had a minus and a plus voltage. Yeah, as soon as I disconnected that power resistor. Now the positive is still a bit high in comparison to the negative. So the negative, let's say, if the negative is minus 1.1, let's say, the positive is plus 1.5. Okay, but that could be due to the fact that there is no load, or much less load on the positive side now that I disconnected this part of the amplifier effectively by removing this power resistor. So I'm beginning to think that part of the problem is in fact the power regulator here, the 7805. Okay, just to show you what I finished explaining to you a moment ago. So I'm still feeding the amplifier with only 70 volts AC. Okay, so there's now power on the amplifier. So let's measure the voltages now. Okay, so this is the positive side. Okay, that now measures plus 1.158 volts. Okay, so effectively 1.15 volts, let's say. Okay, positive. Now let's measure the voltage on the other side. And that's minus 0.78. Okay, so let's say almost minus 0.8 volts. Okay, whomever installed this 7805 regulator chip, I don't know what he was thinking, but he used like a humongous amount of heat conductive paste, and that's totally unnecessary. Okay, I checked D1 and D2, which are both 1N4148 diode, so a fast switching diode, just to see whether they suffered from any damage. And unfortunately, to measure them out, I had to unsolder them on one end, which is always a bit of a pain, but yeah, so I measured them out, and let's see, how can I do this with 2 hands and not 3? Let me see. So if I measure, say, D1, this is what I get on D1. So 551 millivolts conduction. Okay, and it's the same thing on D2. So yeah, D1 and D2 are good, so I can place them back into the circuit. The guy, or the engineer, or the girl for that matter, who designed the PCB, was actually a very clever lad, okay? Because, and I'll tell you that with a little bit of a drawing, what he or she actually did was design the PCB in well-defined blocks, functional blocks of ICs. Okay, so what do I mean by that? You have the block on the PCB, which is this part here, which represents the power supply and the end stage of the amplifier. Okay, so that's this part here. Then you have a second block, which is this part here, which are 4 op-amps, which are used mainly for filtering of sound. Okay, and then you have a third block, which is this block right here, with 1 op-amp right here, which does some of the preamplification of the input, the signal input. And you have this chip here, which is a rather special chip, which contains basically, you could say, solid state switches. Okay, so 4 analog signal single pole switches in here. So this is the third block. Now what the engineer did was separate each block on the PCB via wire bridges, and I made a little diagram to explain to you what I mean by that. So at the power supply there's a common ground, let's say, and then you have a minus voltage and a positive voltage rail that exit the power supply. Okay, and basically those power rails are either minus 15 volts or plus 15 volts. Okay, now via wire bridges, that voltage is transported to, let's say, what I call block 1 on the PCB, which is this block here. Okay, and these wire bridges here are in fact those two right here, just at the exit of the 2 Zener diodes. Okay, now remember I measured the voltage here, which was way too low, much lower in fact than what it should be. Well, once I disconnected these bridges here, the voltage actually went up. So if I measure there, what do I get? Minus 5.3 volts. Okay, now if I measure on the positive side of the power supply, so at this Zener diode here, I get plus 5.31 volts. Okay, so minus 5.32, positive 5.32. So what does that tell us? Well, there must be a short circuit after these wire bridges here. So in effect, on the diagram, I disconnected these 2 wire bridges, so somewhere in block 1 or block 2 there must be a short circuit which pulled the voltage really low, yeah, specifically on the negative side of the power supply. Okay, so you might say, okay, fine, what's the good thing about that? Well, the good thing about that is that, let me show you, Oh, and by the way, you see lower voltages because I'm only feeding about 60 volts AC into the amplifier. Okay. So the beauty of this design is that you can physically disconnect the power supply to one block of chips and another block of chips, which means that it makes it a little bit easier for you to trace any possible problems or short circuits. Now watch what happens to the voltage, because remember, both blocks are now disconnected, because here's the other wire bridge, okay? So it's disconnected, and I only disconnected the negative to block 2, okay? So watch what happens if I reconnect block 1. Okay, let's see. I have to be a little bit careful now. What happens when I reconnect block 1 now? Keep in mind, block 2 is disconnected, okay? So, let me give you a little bit more light. So, and that's the voltage I get when I reconnect block 1. Minus 4.21 volts. Okay? Which I would say is a rather normal voltage drop. If the 4 op-amps, each of them draw some current, the voltage is bound to drop a little bit. Okay? So that looks rather normal. Okay? Now, let's say I reconnect block 2 instead. Okay? So, we go here, and I reconnect block 2. The voltage drops to minus 1.83 volts. Okay, so there's a way much larger voltage drop when I reconnect this part to the power supply than when I reconnect this part of the power supply. So my best bet to look for any possible short circuit would be to look in this part first, and there are a possible number of candidates for short circuits. It could be a couple of Zener Diodes. There are 2 Zener Diodes here, labeled as ZD5 and ZD6. Okay. There are a number of electrolytics here that might be short-circuiting. And then there are these 2 chips here that might be short-circuiting. Now, it is, in my opinion, there is a very high likelihood that it is either the op-amp or the Zener Diodes that are shorting out. Now, I eliminated the DG212 chip, which is the analog switch chip, which sat here. Okay, I took it out of the circuit board, and I put in a 16-pin IC socket in place, just to spare the PCB from being soldered, unsoldered, resoldered, so I just placed in a socket, and I kept so I took out the DG212, and the voltage went up by about a volt at the negative power rail, but that was still not enough in my opinion. So I kept on looking, and in the end, my eye fell when I looked at the schematic. So you'll remember that the power surge came through ground, okay, so, and that it tore through the whole power supply. But if you look downstream, you also see C57 right here, okay, and that is a capacitor which sits at the header of one of the ICs. And which one? Yeah, you may have guessed DG212, the one that I pulled out, okay, and that was causing a lot of trouble. So I pulled out the 100 nanofarad that sat at the head of the DG212 and which sat in fact right here, which is C57, and I replaced it by a 100 nanofarad capacitor. Unfortunately, the only type of 100 nanos I had right now is 630 volts, not 63. But when I put in this capacitor, the voltage at the negative rail went up even more. So now we're only short by about 700 millivolts. So a bit more than the voltage drop that occurs here. So let's say it's acceptable, but it's still a bit too much in my opinion, but it's acceptable. Now, I did measure all of the resistors, all of the diodes. I replaced all of the electrolytics. So, you know, which could it be? It could still be one of these tiny capacitors here, these yellow ones. But in my opinion, it would be more efficient now to just wait until I have all the replacement chips, and then I can install them and then start measuring more accurately with a signal generator and an oscilloscope, I think, rather than, you know, desoldering and measuring and all that. Well, here it is, completely repaired and revised. So the only thing I need to do now is clean up the PCB on the underside a little bit, because there's still some solder flux left here and there, and then connect up an instrument, I would say guitar, and then see what the amplifier will do once everything is connected up. Now, a few remarks. This amplifier comes with a symmetrical power supply. Okay, so according to the schematic, it has a plus and a minus 15 volt power supply rail. Okay, so let me show you what I mean by that. So if you measure from the ground lead to the output of the negative power rail, so which is the output of this Zener diode, you measure in quiescent state about minus 13 volts. On the other hand, you measure about plus 12.2 volts positive. So the power rail isn't exactly precisely symmetrical, okay? So forget about that. Also, the two capacitors that were originally mounted here, yeah, were rated for 16 volts, and after a few measurements, I noticed that there were spikes in voltage, especially when you switch on the amplifier, and those spikes went way beyond 16 volts. Yeah, something like 30 volts or so. So I replaced the original 16 volt capacitors with two 50 volt ones. As you can tell, okay, they are quite beefier than the previous ones, and these should be able to take spikes of 30 volts or even more. Yeah. So also, once the amplifier has been on for, say, half an hour or so, it gets quite toasty here on this or over this heatsink. Okay, so yeah, it gets really toasty. But yeah, it came like this out of the Marshall factory. So I suppose, they gave it some thought as to what sort of a heatsink it might need. But yeah, so it gets pretty warm. Also, remember this type of amplifier, so the MG30 DFX, doesn't come with a fan to cool it off, which in my opinion is a bit of a pity. Had they less skimped on parts, especially a fan, I think this amplifier would last a lot longer. But there you go. That's how they built it at the Marshall factory. Also, clearly somebody had worked on this amplifier before me in the past and had replaced the op amps on the board with some unknown type, at least to me, and whereas the how should I say, the schematic calls for TLO's 72 op amp, and so I replaced the op amps that were broken anyway with TLO 72s, which does seem to work pretty good. Yeah, there's no problems there. There are no problems there. Basically, yeah, what I did, so to recap, is I replaced all the electrolytics because I didn't trust them. I mean, after such a huge power surge, an electrical power surge that went through the whole amplifier, I just couldn't trust the electrolytics any longer, so I just replaced them all. There were, unfortunately, a few more parts that that suffered from that power surge, and more specifically, these capacitors here. Okay, so these are replacements, but they were original capacitors like these. Yeah, so if I'm not mistaken, this was a 220 nanofarad, 63 volts, and that was a 10 nanofarad, 63 volts. And I maybe 100, yeah, 100 nanofarad, 63 volts originally. So I replaced these with Mylar capacitors, and that seems to work just perfectly. So yeah, there you go. 3 out of the, no, excuse me, 4 out of the 5 op amps were replaced by TLO 72s. And that's about it, I would say. Oh yeah, and as you know, as you remember, I also repaired some of the traces on the board, okay, where the power surge had ripped through. So actually some of the traces here were physically blown up, blown away. So yeah, I repaired that, and there you go. That's it. The amplifier is repaired and finished. So let me just clean up a few things, button up a few others, and show you what the result looks and sounds like. And here's a nice panoramic view of the cleaned PCB of the Marshall MG30 DFX amplifier. Actually a quite nice PCB. And now I have to mount back 14 nuts like these, or nearly so, all over the width of the amplifier. Nice. Well, keep in mind I can't play guitar, okay? I'm just going to strum a few strings to give you an idea how it plays when it's, say, about half strength. There you go. And this was only at half volume. Okay. So imagine what it will give at full power. Nice.
Well, this is it for now. We hope to welcome you back for our next episode. But for now, I, Julie, and Technomora wish you a nice day and thank you for watching.